Hey there, everyone. So this is video number 2 of section 2.3. And so just a quick sort of reference. So following the schedule posted on Canvas for week 3, you should be watching the section 2.3 and the section 2.4 videos today. Both sections are relatively short, and so it made sense to group them on the same day. And today we're going to sort of just talk about what we talked about last video and in section 2.2. That is sort of this idea of matrices being invertible. But we're going to talk about sort of this notion of being invertible a little more in the context of linear transformations. So we're going to let A be an n by n invertible matrix, and we're going to let T be the corresponding linear transformation defined in the way that we've usually been defining it. That is, T of x is equal to A times x. And so, given what we already know from the invertible matrix theorem, what are two things we already know about T? Well, we know that T is onto and T is 1 to 1. And that's important for the definition we're about to define, and I'll explain a little bit about that in a second. But, so, we know those two things. So now let's define what it means to be invertible. I'll show you that this linear transformation T is invertible. It's not going to be a big surprise as to what the inverse is going to be. But it turns out that it ends up, sort of, I guess, corresponding very nicely with matrices being invertible. So, linear transformation T from Rn to Rn is invertible if there is a transformation S from Rn to Rn such that T of S of x is equal to S of T of x is equal to x. So this definition of a function being invertible might seem familiar because this is basically the exact definition of what it means for a function to be invertible. And so notice for each of these two sort of composite functions to make sense, well, not to make sense, but to, in order for this to hold for all x in Rn, which it has to, T should be 1 to 1 and onto, right? So if T was not onto, then, well, this part of it wouldn't make sense, right? Because I could find some vector in the codomain that would map in here, but then T wouldn't be able to send a vector back. And so maybe I'll take a step back from that and draw what I'm talking about. So in pictures, and math is much easier to do when you're drawing pictures, if such a function S like this exists, then what there should be is some function S which maps back for each vector AX. So what should happen is I should start with X, T should map it to AX, then S should map it back to the original vector X. And so if T is not onto, I might sign some vector here which S maps into Rn over here, but T can't map back to the original vector. If T is not 1 to 1, then we sort of get this like conflicting information where I've got two vectors mapping to the same vector over here, and S isn't sure which one to map back to. So for this definition of inverse to hold, T better be onto and 1 to 1, which we already know it is. But so if a function S like this is going to exist, well, one seemingly logical way to define it is like this. All right, well, let's check. Is this the inverse of T? So notice the way we've defined S, T of S of x is equal to A times A inverse times x. A times A inverse is the identity matrix. And so those cancel out, and same with number 2, those cancel out. And so it turns out the inverse of a linear transformation is exactly just the transformation defined by the matrix inverse. So not super surprising, but still good to state. What more, though, in the context of linear transformations, we just showed exactly when a linear transformation of this sort is invertible, right? That is that since every linear transformation has a corresponding matrix, well, it's only ever going to be invertible if the corresponding matrix itself has an inverse. And so what I'm going to do is state that formally as a theorem, and then we'll finish off with one example. All right, so let T from Rn to Rn be a linear transformation. Then T is invertible if and only if the matrix A that corresponds to T is itself invertible. And the unique inverse of T, T inverse of x, is just equal to A inverse times x, where T inverse is the inverse of T. So again, this says not only do we sort of have this nice matrix inverse property, we can use the fact that every linear transformation corresponds to a matrix to describe exactly when a linear transformation is invertible. So that means we can solve a problem like this. So if we're given a linear transformation defined in this way, not necessarily as a matrix, and we're asked to find T inverse, well, we know how to do that now. So to do this, well, first we're going to have to find the matrix corresponding to T. And so recall that if T is defined in this way, then whatever the matrix is times x, I should get the following vector. Well, and so remember, from this vector, it's a little easier to extract what the matrix is. right? I just associate each column with a different variable and input the columns sort of going down the row or going down the column. Or you can think of it as sort of just removing the variables and leaving the leftover matrix. And so we know how to find the inverse of a 2 by 2 matrix. So remember, it's the product of the diagonal entries. So negative 5 times negative 7 is 35, minus the product of the two non-diagonal entries, times the matrix where I swap my diagonal, and then multiply the non-diagonal by negative 1. Well, so 1 over 35 minus 36 is just negative 1. Distribute negative 1 through this matrix. And that is A inverse. And so just for the fun of it, maybe we can try to write T inverse in this form. And so that would be T inverse. And so that will wrap up this video. Like I said, we're going to move on to section 2.4 next, so look for that. And I'll see you there.